Oh, what happened here? There you go. All right. So we're starting out here with this is still this is class week 2 and video 2. We'll do some examples with the equivalent spring stiffness. Not a big lift here. All right. So already these this already is kind of like showing you what we're doing. This diagram here where we're showing from here to there. So when we want to collapse those into a single spring, because they are in parallel, they get added together. Because these two are in series, boom, they get added in this way, where they do the reciprocal of the addition of the reciprocals. And we just left K5 as it was. And then, so now we want to merge these two together into a single one. And they're parallel to each other, so we add K5 with the previously added K3, K4 together. And now, here becomes the big ask. Like, is this one and this one, are they in series or in parallel? Well, it's, you know, the bottom line here is, do they share the same force or do they share the same displacement? They definitely share the same displacement. When one goes up, the other, if this goes up right here, this one moves the same amount. Is the force going to be the same? Well, it doesn't have to be the same. It could potentially be the same. If it was the same, it would be in static equilibrium, but there's nothing that has to be the same. So my conclusion, or your conclusion, is that this has to be parallel. It's like it's got the same displacement, boom, boom, boom. It's the same, I'll just write it, it's parallel. All right, therefore parallel. All right, so the equivalent, total equivalent, is going to be K1 plus K2, right? So that's the up here, and we're going to add to what's on the bottom, K5 plus 1 over. Well, actually, we could go ahead and do the little bit of math that we had to do. Do we want to do that? Sure. We'll go K3 plus K. Nope, made a mistake. Sorry. K3 times K4, and there's the whole common denominator thing, K3 plus K4. And then we want to do a common denominator, right? So we can simplify this, because we would like to make it maybe a little more compact, maybe, I don't know. I don't know if this makes it any more compact, but it was like this in the book that I got it from, Inman. So I went ahead and I did it myself. So you take the K3 plus K4 and you multiply it by all of these, K1 plus K2 plus K3, boom. And then you can add K3, K4, and then divide the whole thing by K3 plus K4. And so if you wanted to get the natural frequency of this thing, boom, you'd go K3 plus K4, that's a terrible K, and K1 plus K2 plus K3, okay, oh, I messed up, sorry, I fixed it, caught it, still counts, right? K5. I found my own mistake. But I find that people enjoy finding other people's mistakes, so maybe I should just leave them in there so I can cause joy. Is that a rationalization, you think? I think it is. I don't know if, do you think my new, I put a microphone, a better microphone into this to see if my voice came out any better. I didn't like how it was coming out in my new computer. My new Microsoft, was it Surface Studio Laptop 2, something like that. I don't know. Let's go to do, this video is fairly short, so let's do another example. Can almost do two. All right, so this next example, this is directly out of our textbook, and we have determine the natural frequency of the mass at the end of a cantilever beam of negligible mass. All right, so that's sort of an important thing. We will be fixing that soon, or at least addressing it. So we already saw that the K that we were going to have was going to be 3EI over L cubed, and therefore the natural frequency of this situation here, where we just have a mass sitting on the end, is going to be, as always, the square root of K over M. Not always squared, but often. There you go. We go 3EI over L cubed M. Now, here's what I want to know. Actually, I have written down here on my sheet that I should check the value. I'm like, I wonder if you had a real diving board. Like, it's best that you could. What would be rational numbers? So I said, well, let's take an 150-pound person. Why? I don't know. Swimmers aren't, they're pretty lean people. So I thought a 150-pound man, maybe, all right? So that would be like the weight of the person be at 150 pounds. Let's take the length of the diving board to be 8 feet long. That might be pretty long, but we'll go 8 feet, so that's 96 inches. I looked up on the interwebs and jumped around and found somebody that made the width of a diving board as 14 inches. I saw some that were like 11 and change or something, but anyway, I started with the 14. And I saw one that had a cross section that looked kind of like and it was that was the one that was 14, and it was like 1.5 inches thick right here, and that part right there was was 0.75 inches, and when looking through things, we found out that the area moment of inertia about the neutral axis of this thing was 1.945 inches fourth. Anything else? Oh yeah, this fiberglass, we had an elastic modulus of, looked like it was about the same as aluminum. That doesn't sound right to me, but we're going to stick with it for right now. So that's E 10 to the 6 psi is the elastic modulus that we would use. And we could shove all that stuff in here and see what we get, right? So we would rather have the natural frequency this way, 1 over 2 pi, and take a big old square root thing going on here. You go 3 times 10e6, right? And I could play with the units. I could check my units as I go along here. Oh yeah, I have to do units conversion. Shoot, that's what got messed up here. I'm a units freak. Okay, so you always want to be you got to be careful when it comes to mass in U.S. units, because we have the weight of the person, but we really want to deal with slugs, and slugs are based on feet. So anything that's got inches in it, you have to address that. So there's like, I think you need a 144 in here. So because this is pounds per square inch, so you would need to have 144 inches squared per feet squared. And then let's see, where'd the one, okay, so you have another inches problem here. We might want to, gosh darn it. All right, so that's going to make it even more confusing right in here, because we have 1.945 inches fourth. So I think the solution to this is to just figure out what those units are. I don't think I know how to move that over right there. We'll put that right there. That's in the numerator. We'll go inches cubed right here. So this is 96 inches cubed. That's going to mess everything up. Here's where the mass thing is going to mess everybody up. We could just use the acceleration. Somebody calls these I've heard of these called blobs before. We could divide 150 pounds, and we could divide that right there by 386, but I don't trust it. So I'm going to go 32.2 feet per second squared. All right. So before we go too much further, I'm going to fix the units. I know this makes it confusing. I'm sorry. So first off, we're going to get rid of that, and that turns into 2. Right. So we got rid of 2 of the 4. Now we're dividing by 3. All right. So we're going to divide by inches to the 3rd. So that's going to get rid of 2 of those and 1 of those. So we just have inches at the bottom. So on the bottom right here, we need to have divide this by 12 inches per feet. And what that'll do is put the feet on the top. See if I'm saying this the right way. We'll divide that by feet. Well, we already could have had. No, not a good idea. So that inches would have got rid of the thing, and that would have brought up inches to feet, and that feet would have canceled out. I believe that's going to be correct. All right. So I think you should check for numbers yourself onto this right here. I'll do some other cancellations top into there. Well, not purple. I'm going to put cancellation in there and say, all right, so that's 1 less inch in there. So now I got to think about this feet. Okay, well, first of all, let me get rid of the pounds. Right, the pounds got rid of the thing, and now that's going to bring. Yeah, I think it's going to be rid of feet on the bottom, and the feet are going to cancel out the feet. That feet is going to cancel out that feet, and we're left with 1 over second squared as part of this. I believe so. I'm pretty confident of it. And then when we square root it, we'll have it in the correct units. All right. So I'm going to come up with a number, and then I'm going to maybe pause it and double check my work. Maybe. I don't know. So go to 3 times 10 to the 6 times 1.945. Boom. I'm going to go 96 divided by 12. Gotcha. I guess. All right. 96 divided by 12. Times 150. Divide by 32.2. And divided. And take the square root. And then also need to divide by 2. And divide by pi. Boom. I get the natural frequency is 199.1 or 0.2. See, they didn't do this in the book, so I don't even have any place to check to see if I got the right answer out there. So that's what I'm predicting is the frequency of the thing. And so maybe the period of the thing, which is 1 over the natural frequency, is it's going to be pretty fast, you know. And by the way, this frequency, that'll be the boing sound of the thing, right? Well, this is going to be really small numbers, so doesn't really do us any good. Here's like 0.00. You're not going to be able to measure that. 0.021 seconds. So here's the number that we want compared to it, and we could actually see if we could look that up and find out what note it is. And then maybe get a guitar tuner out and see if we got the right answer when we get it. Yeah, maybe? No? Or is that silly? All right, so how long will we waste? We wasted another 15 minutes. But all right, we'll go to another example after this. Boing.